We know that a magnet can repel another magnet if both are oriented properly. However, if that repulsion force opposes another force, such as gravity, the magnets will be unstable. Instead of floating in space, the upper magnet will flip over, fall down, and stick to its partner. When a single magnet approaches an unmagnetized piece of steel, there is no orientation dependence. Initially, the steel has no magnetic axis. In the presence of an external field, the steel acquires a magnetic moment, always oriented to attract the magnet. This phenomenon is called ferromagnetism. Some other materials show a weaker version called paramagnetism. In either case, the net result is always attractive. Although their origins involve complicated physics, our everyday experience with magnets makes ferromagnetism and paramagnetism feel familiar. Some materials, however, display a surprisingly different behavior. Here is a tiny chip of pure graphite, a couple of millimeters square by a tenth of a millimeter or so thick. When I drop it onto a strong magnet, it seems to take evasive action. The graphite displays a new phenomenon called diamagnetism. It is a diamagnetic material. In the presence of a magnetic field, it generates a magnetic dipole moment of the opposite sign as the steel. Thus, regardless of its original orientation, it is always repelled from a permanent magnet. Here I have a more elaborate setup. 4 small permanent magnets with their north poles arranged up, down, up, down. This arrangement creates a complex magnetic field pattern, but the strength of the field has a minimum point at the center. When I carefully drop my graphite chip onto the magnets, it now hovers at that minimum. More precisely, it falls to a point at which the magnetic repulsion just balances gravity, then is stable to traverse excursions. Motion from that equilibrium point creates a net force back to it, as we see by jiggling the magnet slightly. Magnetic levitation can also arise in the context of superconductivity, but superconductivity requires low temperature, at least as cold as liquid nitrogen. The demonstration shown here is remarkable because in contrast to a superconductor, our sample is at room temperature.